Okay, this is section 2.7 for MAC 1105, and in this section we're going to be talking about inverse functions. And before we begin talking about that, I want to talk about what a function, the characteristics that a function needs to have in order for the inverse to exist. You are going to be given the information in various formats. Sometimes you'll be given a relation, which is a set of points, set of ordered pairs. Sometimes you'll be given the information as a graph. Sometimes you'll be given the information in the form of an equation. Regardless of how the information is given, you need to be able to check that the function you're working with, that you're going to attempt to find an inverse for, that it is one-to-one. And here's what the definition of one-to-one is. Say you're working with a set of points, set of ordered pairs. Each x of the points has to have one and only one y partner. No x value is allowed to have more than one y partner. And the same is true for the y's. Each y value or each y coordinate can only have one x partner, no more than that. So the quickest way to determine that that is actually happening, if you want to know that your x's have one and only one y partner, just make sure all the x's are different. Because if every single x is different, it's impossible to find an x in your set that has two different y partners. So you can make sure that this is happening by just checking that all your x coordinates are different. Same thing with the y's. If you want to know that each y has one and only one x partner, just make sure all your y's are different, because then each y has to have a unique x partner. So this requirement here, which is the definition of a one-to-one function, that has to exist before you can go and find an inverse. That's like your permission to go and find the inverse, because then and only then does it exist. If you're given a graph and you don't have a distinct set of ordered pairs to look at, remember points. It's a set of ordered pairs, but in graphing form, in graphical form. So what you can do to make sure that this one-to-one characteristic is happening when you have a graph, in other words, that every x has a unique y partner and every y has a unique x partner, you can perform both the vertical line test and the horizontal line test, because the vertical line test allows you to check that each x has a unique y partner. And the horizontal line test allows you to check that each y has a unique x partner. Remember that to pass any kind of a line test, the line test that you're performing can only pass through the graph once, and then we say that the graph passes that particular line test. Well, in order for a graph to be one-to-one, it has to pass both of these. And then you know that there actually is an inverse that exists. And then you will go and find it. You could also be given the function in equation form. But remember, equations, if they're functions, they can be, they can be graphed. They can be graphed even when they're not functions. But you can take the equation, you can graph it, and then you can perform the vertical line test and the horizontal line. It's just the horizontal line test. It's just that sometimes the graph is given, sometimes you'll be doing it yourself. Okay, once you determine that your function is one-to-one, that it passes this definition, regardless of how you're going to test that it passes that definition, then the way to find the inverse, if you decide that there is an inverse, is just to switch the x and the y coordinates. That's when you're given a set of points. If you're given a graph, what you can do is find 3 or 4 points on the graph, switch the x and the y coordinates, and then regraph that new set of points so that you have an inverse graph and you have the original graph. And we're going to do some of those as well. Things that are in function form, there's a specific set of steps that you're going to follow in order to find the inverse equation. So in this particular situation, when you're given an equation, and again, we'll do some of each of these, you're going to replace the function notation, the f of x or h of x or g of x, whatever the name is, in the original function with a y. You're then going to switch the x and y. Notice that that is of these procedures, regardless of whether you're handed the information as a set of points where you switch the x and y, or whether you're given a graph where you just pick three or four points off the graph and switch the x and the y. But that is the main essence of what it means to find an inverse if one exists. The main step in all of these procedures is to switch the x and the y, but you will replace the function notation with a y, switch the x and the y, and then you'll solve for your brand new y. And then there's symbols that we use to show when we are finished with those steps that we have found the inverse, and we'll go into one of those. Let's look at some examples here and how to actually determine in each of these cases whether the inverse exists, and then actually how to find it if it does exist. So here's the first way that you can here's one of the ways that you could be given the information. We have 4 ordered pairs here. Notice that all the x's are different. So I already know that each x has one and only one y partner. There's no x there that has 2 different y's partner. So we're good with the x's. Now check the y's. If you want to know that each y has a unique x partner, then just make sure all the y's are different. So we have a 2, a 1, a 0, and a negative 1. So all the x's are different, all the y's are different. This is 1-to-1. So this is a 1-to-1 function because I just tested that definition. Doing too good with this pencil. Okay, so now that we know the function is 1-to-1, that just means we can proceed with finding the inverse. Okay, so this question is, does an inverse exist? Yes. The inverse exists. What is the inverse of the relation? And as it says right up here, this is actually how to find the inverse. You just switch all the x's and the y's in each of your ordered pairs. So we're still going to give a relation, a set of ordered pairs. That first ordered pair was -1, 2. Now it'll be 2, -1. Next ordered pair is -2, 1. So now it'll be 1, -2. Third ordered pair is -3, 0. Now it'll be 0, -3. And the third ordered pair will be -1, -4 when you switch that x and that y. And this represents your inverse. So we checked whether or not one existed, and then we actually found it. Moving on to these graphs. In this particular set of examples, you haven't been asked to find the inverse, just to determine whether or not one exists. There will be a point where you will actually, in some of these problems, a graph that represents the inverse. But for right now, let's just see if you can tell which of these has an inverse. If it does have an inverse, it has to pass, the graph has to pass the vertical line test and the horizontal line test. Okay, so when we draw a vertical line, and we could draw that vertical line anywhere we want, it only makes contact with the graph one time. So it passes. We say that this graph has passed the vertical line test. If I draw a horizontal line, it only cuts through that blue line one time, so we say that this also has passed the horizontal line test. So an inverse does exist for this particular graph. Just weren't asked to find it yet. Okay, moving to the next graph. Anywhere we feel like passing a vertical line, we can do so. You should be able to do it anywhere you want, and it does pass the vertical line test. So we're good with that. However, when you go to do the horizontal line test, it fails it. Any line test that you perform can only make contact with the graph one time as you draw that particular line. So since we failed the horizontal line test, we say no inverse exists, not for this particular graph. Okay, next we move to this shape. It passes the vertical test no matter where you draw the vertical line. And let's see the horizontal line test, it fails because that horizontal line cuts through the graph 3 times. Anything more than once and it has failed that test. So it fails the horizontal line test, and therefore no inverse exists for this particular problem. Okay, moving on to this last picture, it passes the vertical line test, and no matter where you draw the horizontal line, it also passes the horizontal line test. So pass on the vertical line test, pass on the horizontal line test. And since it passed both, yes, we say an inverse does exist for this particular graph. Okay, moving to the next page. Now we're going to look at some different ways that they'll ask us to find the inverse. So we have some examples on the next page. Sometimes they'll be asking you to have a graph and also its inverse. I'll show you what the inverse looks like separately, and then we'll put both of them on the same graph because I want to show you a line test that should always be true once you have your original graph and your inverse on the same grid. Okay, so it's as simple as this. If they happen to name these points, sometimes you're going to be creating the graph yourself, so you'll just pick any 3 points off of the graph that you want to work with. But all it takes is 3 or 4 points. All you have to do is take those points, and as we said on the previous page, you want to find points that are the inverse of the original points. Just switch the x and the y. So the 4, 2 from the original graph becomes 2, 4 in the inverse graph. Likewise for the other 2 points. You had a point -1, 0 on the original graph, which was f of x. By the way, this is the symbol that we use when we're talking about the inverse. We just go whatever the name of the function is, and we use this thing that looks like a little power. It's not really a power. It's the symbol that we use when we're talking about the inverse. So this -1, 0, switch those, and it becomes 0, -1. And then that last pair of points on the original was -3, -2. And by the time you switch the x and the y, then that will be -2, -3. And then you just go and plot these new points in order to get the inverse graph. So that inverse graph is going to be 2, 4, 0, -1, and -2, -3. And then try to just preserve the shape. This just came and curved the other way. Okay, if I take this and put it on this graph, I want you to see something that's going to be true about every graph and its inverse if one exists. It should always be symmetric on either side of a line called y equal to x. Y equal to x is a line that goes right through the origin and has a slope of 1. And if it truly is an inverse and the original graph that you're putting on the same axes, you should be able to crease your paper right on that line called y equals to x, and you should have mirror images on either side when you open your paper. So I'm going to go put that here. Okay, so we had -2, -3. That was one of the points that we just plotted over here. We had 0, -1, and we had 1, 4. Okay, so this was one of the lines, and this was one of the lines. So this line called y is equal to x, which again is a line that goes right through the origin, and it has a slope of 1. That line you should be able to draw right through the center of these two graphs, and you should have matching images. And we do have matching images. On both sides of this pink line, we have an image that goes like this. It's like a V and then comes straight down. See, on the other side, there's the V, then comes straight down. So we have what we call mirror images on either side of this line called y is x. That's always true of any graph and its inverse. Okay, and number 4. In number 4, it says that we're going to graph f of x equal to x squared minus 1, but we're only going to do it for x values greater than or equal to 0. They would like you to graph the original function and the inverse that you're going to get from this. Now let's see if you can understand why have they made this comment regarding x can only be greater than or equal to 0, because they're literally telling you what you're allowed to plug into this function. You can plug in 0 or anything larger. Now I think 3 values will do. You know that this is a parabolic equation. Anytime the x is squared, that's a parabola. So let's see, smallest thing I'm allowed to use is a 0, and then I have to use everything greater. So I'll use a 1, I'll use a 2, keep it small so that my arithmetic is easy. So if I want to know what the y partners are, now you see I'm generating my own graph, which means I get to pick the x values myself, but I still have to abide by any restrictions that are required in the problem, such as this. X values equal to 0 or greater. Now to get the y partners, I just simply do what you always do when you want to find a y partner. You plug it into the function. So if you put 0 in there, it's going to be 0 squared minus 1, that's 0 minus 1, or negative 1. If you put 1 in there, then it's going to be 1 squared minus 1. This would be 1, minus 1 would be 0. If you put 2 in there, then it's going to be 2 squared minus 1, which is 4 minus 1, or 3. Okay, so this would be points on the original graph, just like the problem that I did up above, only I'm doing more of it myself. Instead of them just handing me the first graph, I created the first graph by making a table, and you did plenty of that in chapter 1 and even in chapter 2. So now if I want to get the inverse off of the points that I've already created by plugging into this function, if I want to get the inverse points, then I can just simply switch the x and the y. So this will be my inverse table. I'll still have x and y. I'll still have 3 pairs, and those 3 pairs will come off of the work that I've already done. So instead of 0, negative 1, it'll be negative 1, 0. Instead of 1, 0, it'll be 0, 1. And instead of 2, 3, it'll be 3, 2. So let's plot these original points. Let's hold on to the concept of a parabolic shape. Likewise, when we do the end, it's going to be right here. 0 for x, but negative 1 for y. 1, 0, that would be out 1, 0 units up. 2, 3, that would be 2, 1, 2, 3. Now you can see that what I have here is just one side of a parabola. Now maybe you recall from the first page that any kind of a graph or set of points, or no matter how they give you the information, it does not have an inverse unless it passes the vertical line test and the horizontal line test. So can you see why they said only use x values greater than or equal to 0? Here was my 0 x value, then here were the values that were greater than 0, because that limited the parabola to just half of a parabola, just one side. If they had allowed you to use negative numbers, then you would have a full parabola, fail the horizontal line test, and then there's no problem. Then you can't find an inverse because one doesn't exist. So by restricting the x values, they're creating a situation where the inverse does exist, and therefore you can find it. Okay, so we already have our inverse points. This is just the original graph. X squared minus 1. These are the inverse points. So let's plot these as well. So we're going to go to negative 1, 0. We're going to go to 0, 1. And you can see what's going on here. On the original graph, notice that there was a point that went 1 unit out on the x-axis. Opposite of that, or inverse of that, will be to go 1 unit out on the negative x-axis. Notice that there was a point that went 1 down on the negative y-axis, and now there's a point that goes 1 up on the y-axis, which are in opposite directions. Inverse is like the opposite move. Then we also have 3, 2, so it's 3 up 2. Keep that rounded shape like you use when you have a parabola. So this was the original, this is the inverse. And then if I was to draw that line, y equal to x right down the center, this is called the line y equal to x, and always you have what's called mirror images on either side. So you look at these mirror images. You have this rounded shape and then it goes up. You have the same thing here. Rounded shape and then it goes that way. They're just pointing in different directions because they're on either side of that line. Okay, there is also a question here regarding state the domain and range of each function. So they want you to state the domain and the range for the original function, but also for the inverse function. And I think it's important for you to understand that when you're asked this question, if you're being asked to find the domain and range of the original function, f of x, and also the domain and range of the inverse function, all you really have to do is find the domain and range of the original function, because you switch those two. The domain of this function becomes the range of this function. Remember, the basic essence of finding an inverse is that the x and y's change, they switch responsibilities. So what is the domain here, the x's, now becomes the range over here, the y's, because they're switching responsibilities. Whatever is the range over here, the y values, that'll be the domain over here. So let's just concentrate on finding the domain and the range of the original function. So notice that this is the original function right in here. Okay, so let's look at that graph to figure out what the domain and the range is. Now we can tell that the domain, remember, is the x's. It says it right here. They gave you what the domain was. They said that the domain, and let's try to do it in interval notation, is everything greater than 0. Now if you can't see that in your mind, greater than or equal to 0 would look like this on a number line. We've been practicing a lot of this interval notation. It would look like that on a number line. So if you were trying to state the domain in interval notation, which is the method of choice, you would be going like this. The domain is everything from 0 to 1, or 0 to infinity, excuse me. Okay, it's everything from 0 to infinity, just like this number line shows. And what you're seeing up here in the instructions is the domain for the f function, but in set builder notation. This is a picture of that, a graph of that, 0 to infinity, and this is how you say both of these styles of information, but in interval notation. Okay, the range is very easy to tell by looking at the graph. Remember, the domain is all about the x's, while the range is all about the y's. So if you want to go and look at the graph, you'll be able to very easily tell what the y values are from smallest to biggest. Notice that the very smallest value on this pink graph, which is the original function, is -1, and then those y values shoot to infinity. So everything from -1 to infinity is your range. And I've told you that the x's and the y's, they switch responsibilities between the original function and the inverse function. So this is the domain and range for the original function, and then we're going to do the domain and the range for the inverse function just by switching these. The domain becomes the range over here. So the range for the inverse will be whatever the domain was, 0 to infinity. And the range becomes the domain on your inverse function. So the range was -1 to infinity. And this is your domain and range information for the inverse. So when you're doing some of the problems in MyMathLab, specifically where you're creating them yourselves, you were going to use the graph to look and see what the x values are on the original. The x value here started at 0 and then it swings out wider and wider and wider, but that restriction spoke about it. Sometimes they don't have a restriction in the problem, so you should be able to look at a graph and tell what the domain is. Okay, smallest x value is 0 and then that swings out. I know it looks like it goes straight up, but it actually gets wider, wider, and wider. So we say that goes to positive infinity. And then the y values are even easier to tell on this pink graph. Domain and range for your inverse, they switch. The domain becomes the range, and the range becomes the domain, so that you're really getting the information for both of these with respect to domain and range at the same time you're figuring this out. Okay, moving to the next page. And in problem number 5, which is the last problem, you're being asked to evaluate the composition of functions. And composition of functions was something that we did in a previous section. We're evaluating here again. And we're also being asked to determine whether these functions are inverses of each other. They give you f of x is equal to 2x plus 4, and they give you g of x is equal to x minus 4 over 2. Now this is what's true. Whenever you're trying to figure out whether two separate functions are inverses, this is what has to be true. It's like a little mini proof that you're doing. You should be able to do a composition of f composed of g, which if you remember from previous sections, this is one way to write it, like this. F composed of g, which can also be written like this if you like, with that little bubble, f composed of g of x. You can write it like that if you want. That should be equal to x. Not only should that be equal to x, but you should be able to perform the composition other way around, where g is the outer function and you're doing g composed of f of x. So we take turns with both of the functions being the inner function and both of the functions being the outer function. That way you're doing the composition both ways. Don't forget, this can also be written like this, g composed of f. That's another type of notation for composition, and that should also come out to be x. So this question that they're asking in part B right here, where they're asking, determine whether the functions are inverses of each other, this is how you do that. This is for determining whether two different functions are inverses of each other. Okay, so let's go ahead. I'm going to do part B first, and then we'll go back to A as the easier part, but I'm going to do part B first. Okay, let's see if they're inverses of each other. When you're doing a composition, that's really like plugging one whole function into another. Let's do this one first. When you're going to do f composed of g, you always open up the outer function. Okay, right now we're going to do f. I'm going to write it like this, f composed of g of x. And you can put like a parenthesis around that as well. And you don't really need it like that. Okay, so if I write f composed of g of x, I'm looking for it to come out to be x. And if you remember what compositions are, we're going to be opening up that outer function. Outer function is 2x plus 4. And then what you're going to dump inside of that blank spot is the other function, which is x minus 4 over 2. That's the g of x function. Now, if this comes out to be x, we're halfway there. This is 2 over 1. Here we have 2 in the divisor. Here it's in the numerator, so those cancel. That leaves me with x minus 4 plus this extra 4, and that comes out to be x. So we're good on f composed of g of x. The next thing we have to do, part 2, is we have to prove that going back the other way, doing g composed of f of x, that also comes out to be x. So let's try that now. Okay, so we're going to open up always the outer function, not the inner function. So the outer function is g of x, which is x minus 4 over 2. And in this blank spot a little bit bigger, I'm going to plug in the innermost function, which is this f of x. So f of x is 2x plus 4. And then I'm going to simplify. On the top we have a positive 4 and a negative 4. That goes away, leaving us with just 2x on the top and 2 on the bottom. So that also simplifies to just x. So because f composed of g of x as well as g composed of f of x, since both of them came out to be x, that proves that f and g, those functions called f and g, are inverses of each other. In part A, they asked us to do an evaluation. It said that they want you to do g composed of f of 3. And there's 2 ways to do that. I mean, if you've already done g composed of f, which we did, g composed of f was just x. So we already know that g composed of f, now they wrote it this way. We already know that that's equal to x as an algebraic expression in part A, because we did it right here. G composed of f turned out to be x, but they want us to take what we got as this algebraic expression and evaluate it at 3, which just means plug in 3. So if you plug in a 3 right there, you get 3. So that's part A. That's why I wanted to do part B first, because I knew as part of part B, we will be doing g composed of f, which is what this is. And that completes section 2.7.